And we're live. So, welcome everyone to Climate Chat. I'm your host, Dan Miller, and today we have a special guest, climate scientist George Tselioudis. And George has been working on maybe some of the most important subjects you've never thought about before, and that is cloud feedbacks in the climate system. For the longest time, and actually, I've been involved in climate for like 20 years. I remember going to a UC Berkeley meeting at least 15 years ago, if not longer, where they said, "Hey, we're going to be working on the cloud feedback problem because that's the thing that we don't know in climate science yet, and how that goes could really determine a lot about the impact of climate change." And well, now it's 15 or 20 years later. We're still working on it, but there's been some big breakthroughs, and George has been in the middle of that. So with that, I'm going to first, well, let's see, get some things out of the way here first. First, follow George on Blue Sky. He's on Blue Sky. He doesn't have a lot of followers yet. I think he must have joined very recently.
Yes, yes.
So his link is in the description there, and also there's links to his NASA webpage, to the paper, and to an article about the paper, so it's a little bit easier to understand. And one second, I need to. I had to just turn off a little something there. Got some feedback. And so there's links to the papers, and also follow myself and on Twitter and Blue Sky. And please like the program and follow the channel so we spread the word about climate science and climate action. And one other note before we get started. Next week, our guest is returning guest David Keith, and we're going to be talking about the risks of solar geoengineering and the risks of not doing solar geoengineering. And so that will be a great program next week. So, George, welcome to Climate Chat. Maybe you could start out by giving us a little bit of your background, how what you studied and how you got to NASA and got to be working on studying clouds.
Thank you very much for having me. It's great to be here. I'll start with a few things about myself. I started as a physics major undergraduate. I did my undergraduate in Greece, where I'm from, University of Thessaloniki. And then I got interested in meteorology. So I got into the climate science through the meteorology pathway. There's usually two pathways people usually get into climate science. One is the meteorology, the other is the planetary sciences. After I finished my bachelor's in physics, I came to the US, the University of Miami in Florida, and I did a master's degree in tropical meteorology, which was an extremely interesting subject, especially when you're in Miami doing tropical meteorology. You're right at the source there. So it was a great place to study tropical storms and tropical oscillations, which was my master's degree. At the time, it was near the end of the 80s. The climate change issue, well, it wasn't really yet in the forefront. I mean, it came in the forefront in '88 with Jim Hanson's
Hmm.
Congress testimony. But it was already discussed a lot, and I got really interested. Uh, so I decided to apply to Columbia to do my PhD in climate science. And so I came to Columbia and to NASA GIS, which is a NASA institute located in Columbia University. We're in a Columbia building. And you can do your PhD with NASA scientists who are adjunct professors at Columbia. So that's what I did. I came to GIS in '87. So I was here in '88 when
Hmm.
Jim gave his testimony in the summer of '88. All of a sudden, we couldn't step outside our offices with all the television crews in the hallways wanting to interview Jim after that testimony to Congress. So I was here when the whole thing started, and originally I was planning to study the effect of climate change on hurricanes. But then we realized that the models we have, the model we had at the time was an 8-degree by 10-degree model. And you can fit about 3 or 4 hurricanes within one grid box of an 8-degree by 10-degree model. So it wasn't really a really great tool to study hurricane changes with climate change. So I found another project with Bill Russo, who was at the time here, and he was the first person who started creating a global cloud climatology from satellites. It was called ISCIP, International Satellite Cloud Climatology Project, and it's the first satellite climatology from clouds. So I started by analyzing this very early satellite cloud property results to try and understand how clouds may change with climate change vis-a-vis the cloud feedback issue. Uh, and well, that's how I got hooked on looking at clouds. Plus the fact that it's nice to say when they ask you what are you working on, say clouds. I mean, it's a it's a it's a nice thing to say, but the problem is so complicated that and there's so many things to do and so many angles to look at that it certainly has kept me busy for all this time since the late 80s or beginning
Wow.
of the 90s.
So it turns out that clouds are one of the most important unknowns, well, formerly unknowns in climate science. It was the one that we didn't know which way it would go. If there were more
Mhm.
clouds caused by warming, that would reflect more sunlight and would help dampen the amount of warming we would see. And if there's less clouds due to global warming, that would allow in more sunlight and accelerate warming. And now your paper, looking at satellite data, going back to the beginning of the satellite era. But by the way, I used to work on satellites, my first job out of college, and actually worked on the Landsat, Earth
Whoa.
observation
Mm.
satellite. That was the very first project I worked on, which was a lot of fun. So, but back to this, is that your recent paper uh, titled, let's see, Oceanic Cloud Trends During the Satellite Era and Their Radiative Signatures. That paper has really kind of a breakthrough in our understanding of clouds and climate change. Can you tell us a little bit about what that paper is about, the research you did, and what the findings were?
Mhm. Okay, well, uh, I mean, I wouldn't say breakthrough necessarily. It's a continuation of work by me and other people over the years, and it's becoming more and more interesting and definitive because we're having more and more data. As I was saying, we really started having satellite observations of clouds in the 1980s, beginning of the 1980s. And we didn't even have at the time dedicated satellite observations of clouds. What we had was with the weather satellites that the different nations were using to do weather prediction. And at the time, uh, a group called the ISCIP group, led by Bill Russo here at GIS, started putting together a satellite climatology based on the weather satellites that were flying around by the different nations. And this was a very big undertaking because the different satellites had different, well, similar but not necessarily the same instruments on them that were looking at similar spectral areas, but trying to put all those things together into a global climatology with all the calibration differences was an extremely big task. And so we started really having satellite observations at the end of the 80s, um, which started from the beginning of the 80s. The data set started coming out at the end of the 80s. And we only have this period to analyze in order to see what the satellites have been doing, what the clouds have been doing. So we have about a 40 something year period, 41, 42 years available. So throughout this period, we were analyzing the trends in the clouds, and the trends are hard to extract from the natural variability because the clouds are extremely variable entities. They vary with all kinds of changes in natural variability. El Nino, the Pacific Decadal Oscillation, all those modes of natural variability are changing the clouds. And in order to extract a signal that's related to a long-term climate change, you need a very long time series. So there have been papers before the one that I just published that looked at shorter time periods, and they found some signals. The signals, though, were not as clear as they are now. The advantage of this paper is that I had available all the 40 years of data, and I managed to get a signal that was clearly, it seems to be clearly outside the bounds of natural variability. It comes out of the noise. So this is the interesting thing of the new paper is that we're getting some clear signals, and what the signals are showing us, and I could try to
Yeah,
maybe
you can turn
share
on
some
sharing.
share my screen here.
Yeah.
Let me see if I do that.
And if you have any trouble, I can share your paper as well, and you can just tell me what figure to go to.
Um,
There you go. That's your VPN.
no, that's not the screen that I want to share. I can. That's definitely not.
We'll tell you what. I will try sharing. Let's see. This one here, and tell me if this is the right thing.
Yeah.
Can you? Okay. So that's from your paper. And by the way, links to the paper, which is the paper itself is behind a paywall. So I have a preprint of the paper that's also available that anyone can access. And there's also a write-up, an article that describes the research. So this is figure one. And maybe you can tell us what we're looking at here.
Yeah, basically what we're looking at is a time series of the cloud cover in the Pacific Ocean and the Atlantic Ocean. These are zonal means, meaning it changes with latitude. It's the zonal mean. Latitude is on the y-axis, and year is on the x-axis. So starting in 1983, from this ISKIP dataset that I was describing before, we have the change in cloudiness. With the color scheme that you're looking at, the blue is low cloud cover, the red is high cloud cover. So basically what you're seeing is that the Earth has the well-known climate regimes that we know of at the high latitudes of both the northern and the southern hemisphere. We have the storm tracks, which have very high cloud covers. Then, as we go into the subtropics, we have this very low cloud cover area. This is the subtropical regions where cloud cover is low. And then near the equator and a little bit to the north of the equator, we have what we call the intertropical convergence zone, which is another area of very high cloud cover. So these are the zones that we're looking at here. We're looking at the storm tracks at the edges of and then going inward, we're looking at the low cloud cover subtropics and the intertropical convergence zone. And the trends are showing you how the coverage of those different zones is changing. And well, you see a couple of very interesting things. First of all, the subtropical zones, the low cloud cover zones, are expanding both towards the tropics and towards the high latitudes. So the blue zones, the low cloud cover zones, are expanding, are getting larger. And the red zones in the two the both the intertropical convergence zone is narrowing, and the storm track zones are pushed towards the poles. and some of them are narrowing because they're only pushed from the equatorward side and not from the poleward side. Some they're also narrowing. So what we see here basically is a rearrangement of the basically of the world's climate zones.
Mm.
We have an expansion of the low cloud cover zone in the subtropics, and then we have a narrowing of this intertropical convergence zone in the tropics, and a poleward push, a poleward shift of the storm zones in the high latitudes. So this is a very interesting change in the sense that uh, some of those changes are changes that we're expecting that should happen given the forcing, the greenhouse gas forcing and the climate warming. So the changes are in the direction of what we would expect to happen because of forcing the atmosphere with greenhouse gases and warming the atmosphere. So the fact that we see them now much more clearly in the data makes this a fairly important point, because now we need to understand to what extent this will continue to happen, and to what extent this has some natural variability component to it that will maybe reverse it or change it. So this is the big question here, is whether this is a trend that will continue to happen. And if it is, then it's worrisome in several respects. Most important of which is this expansion of the low cloud cover zones. This is the more worrisome aspect of it. And it is worrisome because these are the zones uh, that a lot of sunlight is coming into the Earth's surface because of the low cloud cover. So these are warming zones, if you want to look at
Hmm.
them in this way. These are warming zones, the blue zones. And those warming zones are expanding, and it appears that they're on track to continue to expand. And then what you may want to call cooling zones, the red zones, again, it's a little maybe
I
counterintuitive that
know.
the
Yeah.
cooling is the red and the warming is the blue. But anyway, the cooling zones are pushed forward, and they seem to be uh, uh, narrowing,
Mm.
both the tropical one and the higher latitude ones. So this is worrisome because in terms of the feedback of the cloud feedback, uh, it appears that the atmosphere wants to allow more sunlight to come in, and restrict the zones where a lot of sunlight is currently reflected away. So this is the worrisome aspect of this, and this is what I'm trying to explore now. Uh, have a second paper that I have in the review process to try and understand what kind of an effect this has on the Earth's energy balance.
Well, that, of course, is one of the key questions, right? Can you give a, well, you must have a rough idea, like in terms of watts per meter squared. This chart starts a little bit before 1985 and ends in around 2020.
It's
Um,
actually goes to 20, yeah,
yeah.
2023.
Oh, it does. Okay. It's a little hard to, okay.
Mm.
Um, And as you just pointed out, we're getting less cloud coverage. It seems to be a fairly steady process, the way these charts look. It looks like it's something that's probably going to continue. But maybe from the beginning to now, what's the difference in terms of how much energy the Earth is absorbing? Do you have a rough
Well,
idea for that? I mean, even from these charts alone, I mean, what it means?
I'm trying to yes, I'm trying to get a number, and I'm using the time since 2000, from 2000 to 2023, because at that time we have actually really much better observations because we have several instruments on the Terra and Aqua satellites, the MODIS instrument that's measuring clouds, and we have the CIRRUS instrument that's measuring the radiative components. And from that, I can try to extract a signal, separate the signal, because there is a signal that is coming from the changes of the cloud properties within the regimes. And then there is a signal that's coming from the expansion of the regimes themselves. So you need to be able to separate how much of the signal that you're getting comes from changes of the clouds within a regime, and how much of the feedback is coming from the expansion of the regimes. What I'm finding is that really what dominates is this expansion of the regimes is what causes most of the feedback. It's a positive feedback. It allows more sunlight to come in. And my calculations are that this is approximately zero point 0.4 watts per meter squared per decade, which is
Doesn't sound like a lot, but
doesn't sound
um,
like a lot, but if you think about it, in in 2.5 decades, you have 1 watt per meter square. In 25 years, with zero point 0.4 watts per decade, meaning that uh, that's about a quarter of the greenhouse gas forcing for doubling of CO2. So it's a significant component of the radiative balance that seems to be attributable to this expansion of the zones. There is also a component that's coming from changes in the clouds within each zone. So clouds are uh, also changing within each zone, and that produces a feedback. The problem with this feedback, not problem, but the fact that this feedback is not important in the global mean, is that a different thing is happening in the low latitudes than in the high latitudes. In other words, in the high latitudes, we find that clouds, for the most part, are increasing a little bit within the regimes, uh,
hmm,
producing a little more cooling, actually, in
hmm.
the very high latitudes. But in the lower latitudes, clouds decrease within the regimes, producing warming. But when you add the two in the
Right.
global mean, the effect of what's happening to the clouds within each regime is smaller, uh, and it's not as important in the global mean as is the effect of the expansion of the low cloud cover zones.
Yeah, so I don't think people understand what watts per meter squared really means. I worked with Jim Hansen on his 2012
Hmm.
TED Talk, and he was talking about zero point 0.6 watts per meter squared Earth energy imbalance. And he said, that's a huge number. And he goes, well, it doesn't sound like that. So he
Yeah,
and I together worked out that that was equivalent to 400,000 Hiroshima-sized atomic bombs going off each and every day. That's how much energy. So you're talking
yeah,
about zero point 0.4, so it's a little bit less, something on the order of 250,000 Hiroshima atomic bombs going off every day. That's how
yeah,
much extra energy is added each each
yeah.
decade. It's been a few many decades, so it's really an incredibly large number. Now, one of the places that this number factors into uh, is the climate sensitivity, Earth climate sensitivity, ECS.
Hmm.
And there's a lot of debate. Believe you were co-author with Jim Hansen on the global warming and the pipeline paper,
Yes.
right? And
Hmm.
that was kind of a breakthrough paper that, I mean, the climate science community, I think, is still having trouble accepting what's in that paper. But one of the key
Yeah.
things, which I guess was partly based on your research, was that the climate sensitivity that the IPCC generally uses is around 3 degrees. In other words, we double CO2 and you have to define how fast the feedbacks are. But within a certain amount of time, not super long time, you're going to get a 3 degree Celsius increase in temperature. In the paper that you co-authored with Jim, the number proposed was 4.8 degrees Celsius, which is hugely larger than 3 and
Mhm.
has consequences for everyone on Earth here.
Yeah.
Can you tell us a little bit about how your current paper, this that we're talking about now, how that what that suggests about the ECS, about this climate sensitivity for doubling of
Yeah.
CO2?
The issue with the climate sensitivity, like you said, is something that is very hotly debated within the climate science community. One thing that happened is that we have these CMIP exercises where we all run our models and we derive climate change scenarios and we derive the climates of the future from our model runs. And and then the models have a climate sensitivity. The previous one that we did, the previous CMIP exercise was CMIP 5, and then the model mean was closer to 3 point, I don't remember what exactly, but near 3. Then CMIP 6 came about, which included improved models in many respects, newer models, higher resolutions, more complicated physics. And then a lot of the models had much higher sensitivity than their CMIP 5 counterparts. So that was a big debate in the community, trying to understand why climate sensitivity has increased so much in the CIMIC 6 models, why the CIMIC 6 models are so much warmer overall than the CIMIC 5 models. And one paper that really tried to identify the reasons for this change was published by Mark Zelinka. Um, I don't remember 2020, 2021. I don't remember what year it was Mark's paper. Um, and he showed that one of the main reasons that the CMIP 6 models were overall warmer than the CMIP 5 models were the way they were treating the clouds in the Southern Ocean. In the Southern Ocean, we have this effect that I was talking about before. There's a strong warming between 30 and 50 degrees south because of clouds, cloud-induced warming, and then a strong cloud-induced cooling between 50 and 70 south. What the CIMIC 6 models were doing is they were having more of a warming in the 30 to 50 south and less of a cooling in the 50 to 70 south. Uh, Mark Zelinga showed that the treatment of the clouds in the Southern Ocean was the main
Hmm.
reason for the differences for the CIMIP 6 models being hotter than CIMIP 5. Then we started checking. The community started looking at the models, the CIMIP 6 models, to see why we have those really hot models. And the reason again was the fact that the clouds over the Southern Oceans. But when we try to compare the models with the observations that we have in the Southern Ocean, the really hot models are doing a way better job in in treating the clouds over the Southern Ocean than the relatively cooler models. Not only the mean properties of the clouds are much better in the Southern Ocean in the hot models than in the cooler models, the seasonal variation, how models change between summer and winter seasons, is much better in the warm models than it is in the cool
Hmm.
models. And this is really important. It's pointed out in a paper by Jiang et al. That came out of JPL recently within the last year, that the the warm models in the CIMIP 6 ensemble are much better in treating the seasonal variability of the clouds in the Southern Ocean than the cool model. So
Hmm.
in some respects, this is pointing to the worm model's doing a better job in a very important aspect. Now, how does this relates to my paper? Well, to the extent again that this is a trend, a forcing induced trend in the clouds, this opening up of the of the um, of the subtropical zone and this uh, poleward shift of the storm tracks. Uh, I want to say that this is several models include that. I had looked
Mhm.
at models double CO2 runs in the past, and especially this poleward shift of the climate zones is there in the models as well. Um, Now, I haven't really tested the period from 2000 to 2023 in the models because the model runs that we have currently stop at 2014. The runs that we do, the AMIP runs as we call them, which are forced with the surface sea surface temperature and the surface sea ice uh, are stopped at 2014. However, there's a new effort. It's called CIRRUS-MIP. It's led by Gavin Schmidt here
Hmm.
at
We had
NASA
Gavin on
GIS.
here.
Yeah, to
Hmm.
extend the models to 2023 with the forcings that the best available forcings that we have until that period. Then I'm going to have um, a really nice tool to see how well the models are doing in reproducing what I find in the observations and which models are doing a better job, whether the hot models, the higher ECS models are doing a better job of reproducing or the low ECS models and all that. So I don't have an answer yet to that. It's an ongoing process. I'm waiting for the runs from the Cirrus MIP project to be able to see which how this effect that I see mirrors itself into this ECS debate.
So just to repeat something you said earlier, because just to make it clear to everyone, you say that the CMIP models, these climate models, you run them and you could look at the future, but you could also look at the present and you could look at the past, at what they quote predict for the
Yeah.
present and the past. And what you're saying is that the models, the newer models that showed more warming, the higher ECS, those models did a better job of predicting the present and the past. And not, so ignoring the future for the moment, but the ones that obviously do a better job at showing what today is like are
Of,
probably better models because they're doing a good job of current and the
yeah.
past, right?
With a clarification of predicting a certain aspect of the present and the past, meaning the
The cloud.
behavior of clouds over the
Hmm.
Southern Ocean, the seasonal change of clouds over the Southern Ocean, or the mean properties of clouds over the Southern Ocean. So,
Okay.
but the Zelinka paper showed that this is an important component of the ECS of the model. How you treat the clouds over the Southern Ocean is an important component of your ECS calculation, and it the Zhang et al. Paper, the recent paper, showed that the models with a higher ECS do a much better job of treating the Southern Ocean clouds and their variability than the low ECS models.
Now, we should point out that your paper actually is fundamentally not based on models. Yours is based
No.
on observations. You
Yeah.
took satellite data of the clouds and you looked at it over decades and you saw, and that's what this chart shows, that the clouds have been decreasing in certain key zones and over time. So this is not, people like climate deniers like, oh, it's models. We don't trust models. No, this is observation. We're seeing this
No,
happen.
this is totally observationally based. Yes.
So,
There's no.
so back to the ECS, the global warming, the pipeline paper said 4.8. Would you say, without maybe being, first of all, Would you still stand by that number, or would you say that your paper is sort of supportive of a number in that area?
Well, in the sense that the paper is pointing to a potential positive feedback, meaning a feedback that increases the warming,
Hmm.
yes, it would be supportive of higher ECS. Now the question is, well, do the models have this feedback in them already? So I don't know the answer to that. This is what I need to test
Right.
now, is whether this observational change that I see is included in the models in the right way or not. And if I find that it's included, it will be included to some degree or other. But what I want to test is whether higher ECS models are reproducing it better than lower ECS models.
Hmm.
I don't know the answer to that until I
Your next
analyze
paper.
the. Yes, there's always material for more work. That's for sure.
So last week we had on Leon Simons, who you were a co-author with on that Global Warming the Pipeline paper.
Mhm.
And of course, Leon's work is on shipping and how the reduction in shipping aerosols through the International Maritime Organization passing rules that ships had to use fuel with 80% less sulfur in it starting in 2020. I guess it started 2015, but by 2020 they had to do this very strict limit. And his work shows that reduction in aerosols led to a reduction in clouds over the North Pacific and North Atlantic, specifically where most of the shipping is. And that has led to a very dramatic increase in global warming over the last couple of years. And so, my question to you is, how does that work fit into yours? Because these are not like mutually exclusive. Like you could have a big shipping impact and clouds could be decreasing over time, right? But
Yeah.
tell us a little bit how you think that work, which we heard about last week, fits into your work.
Yeah, I think what you said really puts it in the right context. The work with the shipping aerosol emission reduction is something that refers to the period from 2020 on, for the most part. The restrictions from 2015 to 2020 were just near the coast, and we don't know whether some ships decided to do it just near the coast or in the middle of the ocean as well. But anyway, from 2020 on, the restrictions were for the whole
Ocean.
area of the shipping routes. So the large changes that people are looking at for the shipping emission reductions refer to the last 3 or 4 years, where those uh, shipping reductions would start to take effect. What I'm looking at is a trend that I'm looking at over the last 40 years. Um, it's a you can see it as the background trend. Basically, this change that I'm trying to extract, I'm trying to extract it from the noise of natural variability. Natural variability changes clouds very much. A lot of things change clouds. A lot of parts of natural variability. The El Nino, for example, produces a wave train that changes the atmospheric circulation, the southern oscillation. And we've had several big El Ninos over that time period. The Pacific decadal oscillation, the PDO, is changing the clouds, is changing the circulation as well. So there's a lot of natural variability embedded into this shift of the cloud zones that I'm looking at. And you need a large data set. You need at least 20, 25 years of data to extract this trend out of the natural variability. For example, if I restrict my analysis to the years from 2000 to 2013 or 14, I don't get a clear signal. I need to extend it all the way to 2023 before the signal really comes out of the noise. So what my work is showing is that the in the long run, there is this shifting of the storm tracks poleward, and there's this shifting of the climate zones with the increase of the low cloud cover zone. Uh, Now, how is that relating to the last 3 or 4 or 5 years where we have this shipping issue? Well, this means that this reductions in aerosols are happening in a background of a change in the climate zone. So
Mhm.
the effects are additive, and I haven't really explored this, and that's something that, I mean, I can only do a few things at a time. That's something that I want to explore. There is an important component to this because when the atmosphere is extremely stormy, when you have a very strong storm, the atmosphere doesn't really care so much about the aerosols at the surface. The atmosphere is going to make high, thick clouds regardless of how much seeding it has available from the aerosols. Where the aerosols are important is when the forcing of the atmosphere is weak, because then we cannot make clouds unless the seeding from the aerosols exist. This means
Mhm.
that since these storm regions are pushing poleward, they open up an area where the shipping aerosols would have become more important had they been there and not being reduced by these new regulations. So to some extent, this shifting of the storms may add effectiveness or efficiency to the reduction of clouds from shipping aerosols. Now, this
Mhm.
is, as I said, is a hand waving argument. You can see my hands waving here because that's what this is. I have no I haven't made any calculations to try and see if that's true or not. I'm very tempted to do some calculations soon to see how much of an effect
Mhm.
this shifting of the storms would have on the efficacy of the aerosol reductions on clouds. But that's going to
Yeah,
be something for the future. But the
Jim.
two are by no means, the one is more a long-term background of changes. The other is a shorter term, faster change over the past few years. And the two are happening at the same time and at very similar places. So
Right.
if
Well, except there is a difference in that your charts you're showing in both the southern and northern hemisphere, the cloud bands are getting narrower.
yeah,
Uh, but most of the shipping is in the northern hemisphere.
yeah,
So what Leon's work is showing is a dramatic change, a heating of the oceans actually in the north and North Atlantic and North Pacific. And so
yeah.
maybe in a few years, your data, if you get to continue it out a little bit, you'll see, it won't be similar to both the north and south. Maybe you'll see a change in the north that it's not quite, or a faster change in the north than you see in the south.
Mhm. Yeah, we already see a faster change in the north and in the south in the radiation
Hmm.
because yes, the clouds are changing similarly in the south and in the north, but in the south, the change is from very high, extremely high cloud covers to somewhat lower cloud covers, going from 85 to 80%. In the north, it's going from 65 to 60%. And that has more of an effect on the radiation when you do
Hmm.
the radiative calculation. So for me, even in my method, it's expected that in the northern hemisphere, those shifts are more effective
Hmm.
in the radiation than the shifts in the southern hemisphere.
Right. I guess a simple way of saying it, if it was very cloudy, usually over the North Atlantic and North Pacific, then the fact that ships make clouds wouldn't make much difference.
Yeah.
But if there's not a lot of clouds in the North Atlantic and North Pacific, then the fact that ships make clouds would have a much bigger impact because they're going to be clouds where there weren't clouds before versus clouds layered on top of each other.
Yeah,
So that's really important. So
that's the and simple way to say something that I just tried to say in a much more complicated way. Yes.
Um, so, in my mind, this paper, it's not getting a lot of coverage, certainly in the mainstream news, but this is something that's actually going to affect all of us. This is going to, so I guess another question is that you hear a lot of predictions for, in the IPCC, let's say, in 2100, under current policies, we're going to hit 2.7 degrees of warming. And that's one of a typical number, I think, that's been, but those predictions don't account for your research, right? I mean, they had older models where, I guess, by the way, did they just leave out the clouds because they didn't know what it was? Like in the IPCC, when they're doing those kind of
No,
calculations, do they just leave
no,
out cloud feedback so they don't know what they are?
no. Clouds were always there, ever since the first IPCC, but they were there in much simpler parameterizations or for formulations. I mean, okay, if relative humidity goes above something, make a cloud here and give it some properties arbitrary. Now we're trying to create clouds in the models from first principles, meaning, starting from the droplet and building the cloud through microphysics and all that. So the clouds in the models now, the models always had clouds, because if you didn't have them, the planet would be
Of
boiling.
course.
So they always had to have clouds, but the clouds then were extremely simple and, of course, not trustworthy at all in terms of how they would change in a warming climate, because we were prescribing everything to the clouds at the beginning. But now the clouds are a lot more trustworthy because we build cloud parameterizations that start from first principles of cloud microphysics, from the droplet level, trying to build the cloud. So now you can trust the models a lot more vis-a-vis the clouds than you could in the past.
But your data, though, showing this positive cloud feedback of it's like 1.5% per decade, or zero point 0.4 watts per meter squared per decade. Um, that's new, right? That you just came out with your paper on that. So my
Yeah.
question is that information that's obviously not incorporated into the past IPCC predictions?
Well, it's not incorporated as a recipe to it, but it may be in the models through their own cloud algorithms. So that's why I say I have to test the models from this cirrus MIP exercise, which will reproduce the climate from 2000 to 2022, and see if it's included in the models. The models may reproduce this shift by themselves without that shift being given to them as a recipe. They may reproduce it because of their own cloud microphysics and
Okay.
their own dynamics. So I don't know if the models have or do not have it, and I do not know if the warm models have it better than the cold models do. So unless I get my hands onto the model runs, I'm not going to have the answer to that.
Okay. Um, okay. Um, let's see. So now at some point, I guess, if all clouds went away, then everything would equal out. So I guess I don't know how to ask this question, but we saw the trend. It seemed very steady, like just like a cone that was straight
Mhm.
lines going up. Um, there must be some limit to that. What's your thoughts on what the future trend will be? Do you think it's going to continue that steady kind of, I'll call it linear um, expansion zones? And then by the way, the equatorial one was narrowing down to zero. Well, it's not really zero. I guess it's
It's not really
narrowing down to
zero.
a certain percentage cloud cover. Do
Mhm.
you see that continuing? Do you think over the next, let's say, couple of decades?
Well, as I said, subjects for future work. I don't know the answer to that. There may well be a limit to the expansion of the subtropical zone, or a limit to uh, the um, the narrowing of the storm zone. It may well, equilibrate at some point and just remain constant, because um, these are all dynamically driven cloud changes, I believe, and what happens to the atmospheric dynamics, and how much the zones can be squeezed in a sense. It's something that we need to study in detail. If I give you an answer, I'm gonna regret it a year or two down the road when somebody, does the analysis and finds that it's what I said is wrong. So, or I'm gonna try to do some of this analysis to try and understand what's limiting this expansion of the zones. There may well be a limit, and it may just flatten out and not continue in the future. I don't know the answer to that right now.
Okay. Well, it's important. Let me ask you. We're gonna open it up to questions, and I'll start off actually, and before asking Stacy for hers. But Doug Grant in the Zoom comments asked, "How does your data correlate with the recent paper on albedo, where they measure Earth shine on the dark side of the moon?" Because that I would assume this is all changing the overall albedo of the Earth. Has
Yeah.
this been sort of correlated with other data like that? Your work?
I don't know I mean, I was aware of some Earthshine works in the past. I don't know what the latest is or what the result of the latest one is, but we have excellent measurements of the Earth's albedo thanks to the Cirrus project,
Hmm.
uh, and we do see a big reduction in the Earth's albedo over the past uh, 30 years. I mean, not no, the series starts in 2000. Over the last 23 years, if that's what the Earthshine data also shows, then they agree. But I don't know what. I'm not aware.
So, okay, so we have the series data, and that shows albedo. Um, is your research or your paper, is that enough to account for all of that albedo change? In other words,
No,
okay, so that's part of it then, but
that's
it's
part
not
of
all
it.
of it.
No, it's not all of it. It's part of it. It seems to be that if you take it in the global mean, it can be a big part of it, because some other parts are canceling between the high and the low latitudes. So some other
Hmm.
cloud changes are contrasting between the high and the low latitudes. So they cancel each other. While the effect that I see is narrowing of the storm zones, both in the tropics and in the high latitudes. So there's nothing canceling each other. So it comes out very significant in the global mean, uh, while some within regime changes seem to be canceling between high and low latitudes and are less important. But it doesn't, no, by no means does it account for the whole thing. And I wouldn't expect it to.
Okay, so I'm gonna say if um for the audience out there, if you're listening on YouTube and you have a question, please put it in the comments now and preface it with the word question so we can easily spot it versus just a general comment. And the same for Clubhouse and on Zoom. And if you're on Zoom and want to ask a question live, you can also raise your hand. But now let's bring in Stacy, our co-mod, and see if she has her own question or a question from the audience. Welcome, Stacy. Hi there.
Dan, thanks, George, for being
Hi.
here. I have been saying for quite a while, I want a cloud expert because I don't really get the interplay of, do they help us or do they hurt us? You know, and I guess it's always and it depends when and where.
Mhm.
And to that point, there's been some chatter, and I will correct everyone. It is not chemtrail, it is contrail. It's about condensation from the aircraft or spacecraft that is leaving the trail at higher altitudes. So, is there any thought on? I mean, obviously, I asked this similar question last week. Is there any thought? We don't want flying. I mean, I want trains all day long, but we're not getting rid of airplanes anytime soon. Is there any thought to how and when and where planes are flown that might be more beneficial or do less damage from what they're able to do in terms of creating some cloud?
Yeah. Well, it's not a question of where, it's a question of fuel. I mean, there have been, similar to the shipping industry, there have been discussions about fuel changes in airplanes. There's fuels that produce less water vapor that eventually turns into cirrus clouds, which have a warming effect on the climate. So there have been discussions. I haven't followed them, and I don't know where they are, but similar to the discussions in the shipping industry that ended up with the regulations that were put in 2020 and so on. There's similar discussions in the airline industry for differences in fluid in the fluid that they're using for. But like I said, I don't know. There's not much you can do in terms of where the planes fly. I mean, or what routes they follow. That's not gonna make that much of a difference.
I thought you were saying about in terms of the latitude and what is the regional difference versus the whole difference. The
Yeah.
temperature in places and so that whether it's the route they take or, the destinations that we go to, et cetera, when
Yeah,
you're talking about
well,
transatlantic flight or continental.
I can think a little bit, off the cuff here and try to come up with, if you fly closer to the storm tracks, again, what's going to happen is what Dan was saying before. If there's a lot of cloud there already, making more cloud is not making that much of a difference. So flying into clear skies and creating cirrus clouds, that has more of an effect than flying into cloudy skies. So you may want planes to fly more into storms, but I don't think they're going to like that idea, because that probably means more turbulence and more
Tougher passenger experience. Yeah.
yes. But
George,
generally, a cloud that flies in a storm makes a lot less difference to the radiative balance than a cloud that flies in clear skies. So that could be one way to
George,
think
I think this
about
brings up a good subject for you to tell us about, because we think of clouds as they're white and they reflect the sunlight, and that's true, and that helps cool the earth. But clouds at nighttime act as a blanket, not letting the earth radiate energy out into space, and that keeps the earth warmer. And some clouds, even in the daytime, have a
Yeah.
net warming and a net versus a net cooling. Can you just give us, a high level brief tutorial on clouds, what makes them cool and what makes them warm the earth?
Yeah, well, that's what makes, I mean, that's one of the many things that makes clouds very complicated, is that they both reflect sunlight and they trap heat at the same time. So they work both as reflectors, which cool the planet, and they work as basically greenhouse elements
Blanket.
that blankets. Yeah, that's why we say that when we have a starry night in the winter, it's always colder, because at night they only warm, given that there's no sunlight. Clouds are a warming factor at night. During the day, it all depends on how thick the cloud is. If the cloud is very thin, and particularly if the cloud is a very high thin cloud, meaning we call them cirrus. So if you have thin cirrus in the upper troposphere, They don't reflect very much because they're thin, so they let a lot of the sunlight in, but they are very good in blocking the heat. So the very thin cirrus clouds are warming elements. These are the types of clouds that contrails are made of, is thin cirrus clouds high in the atmosphere that do mostly blocking of the heat. They don't reflect as much sunlight. However, if they start getting thicker, then the reflection increases and then there's a balance. So there's a certain optical thickness of the clouds after which even the high clouds are becoming a cooling element. But during the day, if you see really thin, crispy cirrus clouds high in the atmosphere, those are warming elements.
Okay.
I had heard a talk once where they were talking about not the fuel as the reason for the contrails, but the skill of the pilot at times, how they fly the plane, because they gave the example of and now maybe that may be a fuel thing that they overlooked. In the military, when you're flying, you do not want to leave any evidence that you have been there oftentimes. So, or most times. So they are trained so that they fly the plane in a manner that does not leave the contrail. I don't know. Have you heard anything about that? I don't know.
No, I haven't. It makes sense the way you're saying it, that if they want to avoid detection, of course they don't want to have contrails. But how do you do that in a commercial airliner? I don't know.
Yeah, so George's paper's not really about contrails, so we should move on to others. Are there other ones in there?
There are, but I haven't got through them all, so I'll stop back. Thanks.
Okay, we'll ask Eli to join. Hey, Eli, what's your question for George? If you're there, Eli. Let's see, is Eli still? Yep. Okay, well, maybe Eli. Oh, maybe you're not co-host anymore. What happened there? Okay, I'm going to now. Okay, now you should be able to unmute. Sorry, I don't know what happened there.
Thanks. Okay. So first I want to go back to a couple of things that you mentioned just to kind of emphasize some points that you made. You mentioned 0.4 watts per meter squared per decade, which it comes as a bombshell, at least to me, because if you look at the increased radiative forcing due to increases in greenhouse gases, that's 0.3 watts per meter squared per decade. So if that's the case, the feedback from clouds on all of the greenhouse gases that are in the excess greenhouse gases that are in the atmosphere, that is not as much. That is the increase of the cloud feedback is higher than the increase in greenhouse gases, and that's pretty remarkable.
Yes, I must admit that when I first did the calculation, I repeated it a couple of times to make sure that I'm not doing something wrong. I mean, globally, it's around. I gave you a it's around 0.37 watts per meter squared per decade is the calculation. So I agree with you. Like I said, when I first did the calculation, I repeated it a few times to make sure I'm not doing something wrong, but I don't think I am.
Yeah, and so this is, we're at a point where the natural response to the radiative forcing that we've caused is in fact larger than the growth in the directly caused radiative forcing due to increased accumulation. Okay, so the other thing that I wanted to highlight and emphasize is you were talking about the increase in clouds at higher latitude versus the effect of aerosols. on radiative forcing, and you mentioned how that is perhaps obscuring the changes in aerosol forcing due to changes in shipping fuel emissions. So if I summarize that by saying that clouds have been masking the amplitude of the aerosol feedback. Would that be a correct statement?
In a way, yes. I mean, on the other hand, clouds are a large component of the aerosol feedback. So what I'm saying is that there are specific cloud regimes where the feedback is much more important than in others. So if you have a mid-latitude storm, for example, where you have very strong forcing and you make very high, thick clouds, the presence of aerosols is not as critical. You're going to make the clouds anyway. But if you have a situation of that is weakly forced, and you make lots of low, thinner clouds, the presence of aerosols is important because it enhances the both the albedo, the reflectivity, and the coverage of the clouds if there's more seeding available.
So therefore, in places where clouds have been diminishing, such as in the tropics, aerosols then would be their effect on the net energy balance would be more important. Correct?
Yeah, but even in the tropics, I mean, if you have a tropical storm, or if you have monsoonal circulation clouds, their aerosols are less important than
Yeah, so
in
it's kind of unfortunate for stratospheric aerosol injection in that we would want to increase the thermal gradient between the tropics and the poles, and this is kind of saying that when you look at the trends in clouds, you're likely to be most effective where you would rather do the least and least effective where you would like to do the most.
Yeah, in a way, yes.
Okay, thank you.
Thanks, Elon. And now, Dr. Brian, welcome to Climate Chat.
Thank you, Dan. And George, thank you for a great presentation today and the wonderful research that you're doing. A couple of questions for clarification. The first is that contrails, to my knowledge, when you change aviation fuels, you're able to affect the concentration of cloud condensation nuclei, but perhaps less so the water vapor. And the second question is that my quick research indicates on the internet that in the daytime, even the thinnest of cirrus clouds tend to reflect light and cool. This is particularly important in the ocean, where the clear albedo is only 0.2, and we're not reflecting much light, versus nighttime, when, of course, it's acting as a blanket. I'd just like to get clarification on those two questions for you.
Yeah, the first question, I mean, the water vapor versus condensation nuclei for airline fuel, I'm not going to comment too much because I'm not an expert on the subject. I was under the impression that water vapor is an important component of the contrail formation, along with condensation nuclei, but I don't know which one is more or less important in creating contrails, and so I don't know what people are shooting at in terms of changing the fuel. Are they shooting at fuel that emits less water vapor or emits less condensation nuclei? I don't. I mean, I haven't followed that literature, so I shouldn't comment on it. The second question is, of course, we have this thing which is the cloud radiative effect, which depends on the cloud, of course, depends on the optical thickness of the cloud, but it also depends on the underlying surface. The darker the underlying surface, the more effective the cloud is and the higher the cloud radiative effect is. So if you have clouds over ocean, they're much more effective in cloud cooling, for example, than if you have clouds over desert, which was going to reflect uh, the incoming sunlight, most of it anyway. So I agree with you, but at very low uh, cloud optical thicknesses, um, the short wave versus the long wave, the heat versus the sunlight part of the cloud effect depends also on the cloud height. If it's a low cloud, even if it's thin, optically thin, it will mostly reflect because it's not efficient in trapping heat because it's already in a temperature that's very similar to the emission temperature of the surface. However, if you have a very high cloud that's thin, uh, it's not going to reflect much, but it's also very efficient in trapping heat because it's at a temperature that's much lower than the surface emission or the mid-tropospheric emission. So then it becomes more effective in trapping heat. So it depends on the optical thickness of the cloud, but of course it also depends on the cloud top temperature or the cloud top height.
Right. Are those summaries over 24 hours? And would you distinguish between the daytime 12 hours and the evening or nighttime in terms of these effects?
The plots that I have on the um, on the paper are annual means, and they include both the daytime and the nighttime effect of the clouds.
Okay. So you might say that during the daytime, cirrus clouds and contrails have a cooling effect, but at nighttime they could have a warming effect.
Mm-hmm.
Okay, thank you. That's particularly important in the poles where you have day for several months and night for several months. And so these alternative aviation fuels, some of which include alcohols that actually improve the oxygenation and decrease the particulate matter and decrease the CCM, those could be effective in the winter over the poles because they would decrease contrails over the poles in the winter. And then there are other additives that can increase CCM and perhaps brighten contrails during the summer daytime in those regions. So it's very interesting to consider for those Arctic flights. Thank you.
Yeah, and now that you mentioned it, I mean, Stacy mentioned before something about changing the routes. Of course, it also depends on the surface that you're flying over, whether it's flying over ice or whether you're flying over in terms of the reflection of the cloud and how that changes. So that, there may be something there, but again, too
Yeah.
much hand waving on my side
Well, no,
for those
as
issues.
a pilot, it's very interesting because pilots have an enormous latitude up to thousands of kilometers as to how they route the flights. So there's actually a lot of degrees of freedom without
Mm.
affecting fuel consumption very much on whether to fly over dark ocean or bright ice or bright clouds. And thus, there are strategies that could be very effective
Mhm.
in the future potentially.
Yeah, there is a researcher that has done work on this that we could invite to Climate Chat someday to talk about. That seems to be a popular subject. But speaking of Arctic, does your paper on cloud changes over time due to global warming, um, either do you think the clouds are influenced by or are the reduction in clouds causing a change in Arctic sea ice?
Well, that's a very hard question to answer. First of all, it's very hard to answer from observations, even from satellite observations, passive satellite observations, because um, well, the surface tends to look a lot like the clouds in terms of reflectance. You can see some satellite pictures. There's an iceberg, and then there's a cloud, and you can see the cloud over the sea surface, and then once the cloud goes over the iceberg, you lose it, of course, because it has the reflectance that's very similar to the iceberg reflectance. So retrieving cloud properties over ice is a very, from passive satellite measurements, is a very difficult task. It improves a lot if you use active instruments like lidars or radars. Then you get a much better picture of the clouds over ice. So now, how the clouds affect ice changes is something that we've been trying to look at. Actually, we have a project where we try to see, okay, if you're, say you're losing the ice, but you replace it with cloud, you're not having much of an effect because, and that's a thinking that exists, that if you have less sea ice, you're gonna increase the amount of moisture availability for you, because you're opening up open ocean, so you have more moisture that can come out of it and create more clouds. And so you're going to lose the ice, but you're going to create more clouds out of the open ocean. So that's not going to make much of a difference. They're going to reflect pretty much equal amounts of sunlight. So we try to see if this is true or not. And the answer is sometimes it is, sometimes it isn't. It's very seasonally dependent. Sometimes decreases in sea ice in the fall would produce more clouds, and reflectivity is not going to change much. But then you go in the summer, and then you decrease sea ice, and you're not producing as much cloud, and so you change the reflectivity. So it's a very complicated process, and we have very poor observations because of this inability of passive satellite instruments to measure cloud properties over ice. The bad thing about the active measurements like lidars and radars is that it's a very narrow beam that only observes a very small region. So you need many years of data to be able to derive statistics that are good enough to look at trends.
Okay. So we're going to bring Stacy back with another question. Welcome, Stacy.
Hi again, and thanks, Dr. Brian, for more eloquently following up my question. I will have to go back and listen because I was compiling questions from YouTube. And I think, Dan, this last question you were talking about is how much does sea ice affect clouds?
Right, we just asked that. Right,
Okay,
both ways.
right. But there's a question of how much do clouds affect polar ice loss?
Yeah, well, that was the last question, was both directions
okay.
on that. Okay.
All right. Then the Nadia wants to know what the new ECS is. Is it 8, 10 degrees higher?
No. I don't think we're anywhere close to 8 or 10 or anywhere higher. Well, ECS is a number, is a construct. I mean, it's an index that we try to use in order to understand what models are behaving as hot models versus cold models. It's not, so it's a relative number. There's been a lot of emphasis on ECS, but and there is issues with that, but I'm not going to go through those now. What I can say is that a lot of the CMIP6 models seem to have ECS near 5 degrees, anywhere between 4.8 and 5.2 or 5.3. And those are very good models. Those are models that are having excellent cloud parameterizations, some of the more advanced ones. And those are, again, as I was saying before, models that seem to be doing cloud changes over the Southern Ocean in a very accurate way compared to what we've been observing. So this would be the upper, at the moment, near 5 or a little above 5 is the upper limit of what I think we consider as acceptable ECS. Actually,
which is pretty high. By the way, I should point out that the paper you co-authored with Jim Hansen where they also came up with 4.8, that was based on paleoclimate. A lot
Yeah.
of that was based on paleoclimate. So what you're saying is sort of the data from the models that are reflecting the actual current conditions, the ones that do that best,
Yeah.
also have an ECS that matches what you and Jim said is the paleoclimate number. So there's kind of reinforcing lines of evidence there.
Yeah.
But
I mean,
I think you were trying to say this, and I think it's important to say because I think the public gets confused about ECS. ECS is just a scenario. It just says,
yeah.
what if you double CO2 and hold it that way, and you wait a certain amount of time, how much would the temperature be? And this is something that Svante Arrhenius did in 1896. He wrote a
Mhm.
paper that said, what if we double? He didn't think we actually would double CO2 or 3,000 years or something. But so the climate's going to do what it does, and this is a number that tells you how sensitive the climate is to changes in greenhouse gases. And it
And it's
turns
a,
out what you and Jim and what this paper even suggests is that the Earth is actually more sensitive to changes in greenhouse gases than we would have hoped it would have
yeah.
been.
Well,
And
it's a number, it's a scenario that actually never going to happen.
right.
So that's why I'm saying that it's a totally hypothetical number. We're never going to get to an equilibrium where uh, we're going to keep CO2 to a certain level. For one thing, the Earth, as you're changing, is changing its carbon absorption anyway. The ocean is changing carbon absorption. The land is, so there's no way you can achieve something like that. So we're using it as an index, as something to have in mind, not as a realistic temperature that the system is going to get to at some point in time.
Well, I guess it's also just saying that we shouldn't be doing this experiment that we're doing to see
Oh
what
yeah.
happens when you double C. We're doing that now. We're doing the experiment, but it's not going to end well. But yeah. So we
One
got
quick,
something else from Dr. Brian. Go ahead, Dr. Brian.
yeah, one quick follow-up on the clouds and ice question. Back in 2012, we had some cloud-free events and associated with soot from fires. This resulted in the melting of 97% of the surface of Greenland. And these cloud-free events have a profound effect on ice because of this insulation during the summer. So these can be very significant in terms of the total melt, at least on alpine glaciers, if not, and ice sheets, if not the sea ice themselves.
Mm-hmm.
But this interaction between Arctic fires, the deposition of soot for creating a dark layer, and the insulation has a profound effect each summer in these regions. So especially in the Northern Hemisphere. Thank you.
Mm-hmm.
Right. So
Uh,
thanks. So
Something else that one other question, and this goes into, I mean, about the shipping and the fuel change that we experienced in 2020. When we talk forward about the potential of solar radiation management, termination events. If coal use disappears, I mean, because there is coal still in use, as much as nations phase it out, there are others that are building and using. If coal use disappears, do we need atmospheric regulations pronto?
you mean solar geoengineering?
Well, or yeah, exactly.
Yeah.
So, yes.
Yeah, you've
What do
done
we
some
do
work
to compensate?
on ozone, I know, and things like that. I don't know, George, to what extent you've looked at SRM. We have David Keith next week talking about it. What are your thoughts on solar geoengineering?
Well, uh, if worst case scenarios materialize, it's going to be a necessity, it looks like. So the question is how you do it. I mean, there's several people who are working on ideas for solar geoengineering. Like I said, if we stay on a worst case scenario, it may well be necessary in sooner than we think. Um, So how do we do it? I mean, stratospheric injections are probably the most looked at or studied method at this point. It seems to me, cloud seeding at the ocean surface is another possibility, or ocean surface seeding for increased carbon absorption. I mean, all those are possibilities, but for me, at the moment, the one that's further ahead in terms of research is the stratospheric injection
Right.
possibilities.
And we'll be talking about that next week, actually. And there's there's actually two, I think, really important papers on that. One is someone finally did the calculations of what's the cost in lives of doing geoengineering versus not doing geoengineering. And the answer was not doing it costs more lives. That David was a co-author in that paper. So we'll talk about that next week. And there's another paper that says that solar geoengineering, if done correctly, could strengthen the AMOC, and certainly we've covered the AMOC a lot on this paper. I mean, on this program. So
I'll be watching.
Okay, so with that, George, I want to thank you so much for, first of all, for all the work you're doing. This is extremely important work. I don't think it's getting the coverage. People don't understand that this, very often research sounds, I don't know, just sounds academic or something. The work you're doing is going to affect all of our lives. It's how much climate change and how much global warming we're going to have. And the clouds, as it turns out, is a huge, huge part of that. We all had our fingers crossed 20 years ago, hoping that cloud feedbacks would help cool the planet. But now with the work you're doing, it's showing that it's probably going to increase warming, not decrease warming, and that means we have to work even harder to get rid of our emissions now and do the other things we have to do to fight climate change.
Yeah, when I entered the field, the prevailing idea was that clouds are going to get brighter and going to reflect sunlight, and they're going to really save us from climate warming. And that was based on very few observations. Then we got the satellite observations and started analyzing them, and then it's then that we realized that wasn't going to be the case.
Perhaps some optimism bias going on back then, which I think climate is littered, I think, with a lot of optimism bias. But thanks for the work you're doing. We're looking forward to the next thing. And actually, I understand you're a co-author on Jim Hansen's next paper coming out very, very soon. And we're going to have Jim on the program when that paper comes out, maybe in January, if it comes out soon. I don't know if you have any update on the release date, but
No, I haven't heard from Jim the last few days, but yeah, that's the time frame. I think sometime early in January. I mean,
good. So we're looking forward to hearing more about that, and we'll hear more about your work when we cover that paper with Jim. So thanks for all you're doing. Keep it up, and maybe when your next paper is done, we'll have you back on again, and we can talk more about the impact that these cloud changes are having in terms of energy balance and things like that. So thank you so much for being here on Climate Chat. And to everyone, again, I want to repeat, George is now on Blue Sky, so go follow him there. He just started, so he doesn't have a lot of followers. Let's get the follow count up. Also follow us on Twitter and Blue Sky. And also, please like this program and please follow the channel so that it's shared with more people on YouTube, and therefore the word gets spread. Thanks, everyone, and we'll see you next week talking with David Keith about solar geoengineering. Thanks, everyone.
Thank you.
Thanks, George.